Hi everyone, welcome to the support session. So in this kind of mini set of slides, I just want to run through the kind of things you're going to get asked in the class test and the kind of things I'm expecting as a response to the different questions. So first thing is just to talk a bit about the assessment itself. Actually, the very first thing is there seems to have been some confusion about where the test is. So to be clear, hopefully this has been cleared up by now, but the test is online. You'll do it from your own home. There is no need to come to the university to take part in the test. So the test will be 3 case studies, and those case studies will be released at 10 a.m. on the morning of the test. And you'll have 2.5 hours to look at those case studies, review the data, write some comments about the case studies and the underpinning physiology, and I'll go through that in a second, and then submit that as a Word document to turn it in. So there's no need to come into the university, and the assessment, it takes place on the same day of the week as your normal lecture or seminar session, although your normal seminar session is scheduled for an hour, and you have up to 2.5 hours. I don't think you'll need the full 2.5 hours, but if you do, it's there. The format will also include an additional deadline of 1 o'clock for those who've got learning agreements. So if you normally have extra time for exams, then you get that extra 30 minutes. If you normally get extra time for class tests, then the extra time is built in. So there will be 2 Turnitin submission points. One that will close at 12:30, and if you don't have a learning agreement, you should use that one. And one that closes at 1 o'clock, that if you do have a learning agreement and it's after 12:30, then you should use that one. So as I had in the email that I sent through, I think it was last week, the test itself is 3 case studies, and each case studies will be a scenario and some data. For each case study, you will need to look at that data, process it, give some interpretation about that data in terms of what it means, and much of that will be based on what we've done in the seminars. In fact, an awful lot of that will be based on what we've done in the seminars. For the second part of each case study, you will need to give some underpinning, your understanding of the underpinning physiology that explains your interpretation, or what the coach is trying to do, or what the aims of someone's training program have been, or how some adaptations have taken place. So part 1 is interpretation. Part 2 is really explaining your interpretation based on your understanding of the underpinning physiology. It's worth pointing out that I am not anticipating these to have references. If you feel it's important to put a reference in, and particularly in part 2, then feel free to do so. But I'm mostly interested in whether or not you can provide me with a strong interpretation of the underpinning physiology. Part 1 shouldn't have any references because it's your interpretation of the data. So I don't need you to cite other work that is that has used similar data. You don't have to go and try and find research that's got the same kind of test and the same kind of athlete and the same kind of outcomes. That's not the point. It's your interpretation. As I say, part 2, you may feel 1 or 2 places may require a particular reference if you're comparing it to norm scores, for example. But other than that, I don't expect masses of referencing in either of these. A few other bits just to just to point out. Part 1 and part 2 are equally weighted. So each part is worth 50% of the marks available for that particular case study, and all 3 case studies are equally weighted. So each case study is worth 1/3 of the overall marks, and each part of that case study is worth an equal proportion of that 1/3. So 50% of the marks for part 1 and 50% of the marks for part 2. There's a word limit for each case study, and that's 800 words. And given the equal weighting, I would suggest you do consider a maximum of 400 words for part 1 and a maximum of 400 words for part 2. So it's not a assignment where you will do well if you just write everything you know about flexibility. Your answers should be targeted to the case study and targeted to the data presented in the case study, and then targeted to those systems that are relevant to that case study. And that's the aim of it. So equal weighting, 800 words per case study, approximately 400 words for part 1 and part 2. Also, it's worth just quickly going over which topics will, or that you should consider might be as case studies. So I said earlier, the topics are all picked from the seminar work that we've done. So that will include flexibility. It doesn't include hematocrit and blood analysis, but it does include VO2 max. It does include data on RER and intensity, and it does include the most recent stuff on strength and power. So the case studies could be something to do with an athlete who has done a flexibility program. It could be trying to interpret some VO2 data from an athlete. It could be trying to understand RER and intensity data and how that relates to an athlete's performance. Or it could be something to do with a particular athlete's strength and power. I'm not trying to trip anybody up, so that the case studies won't be combinations of flexibility and VO2 max and you've got to try and glue them together, or RER and strength and power. They will be on one of those topics, each case study. So if you understand those topics, you should be fine with the case study. The only possible exception to that, and I say possible not because I'm expecting you to do it or I've built it into the question, but if you're answering, for example, an RER and intensity question and you think it's appropriate to start to talk about VO2, maybe VO2 max, then that would be fine. It's much more difficult to separate out case studies about VO2 max and RER because just as concepts they overlap so much. But in principle, each case study will be a standalone case study on one of those topics. Okay, so let's get into the first example to try and take you through the kind of things that I'm expecting. So here's some data, and you may recognize it. This is data that is actually identical to some data that we ran through in one of the seminars. And that's on purpose. We've done lots of calculations in the seminars, and there's a reason why we've done that, and there's a reason why you've got an app on your phone that can help you with all the calculations, and that's because that's been to try and get you to the point where you can do these case studies. So all of our seminars have really been practice sessions for the case studies in one form or another, or at least the seminars have included some kind of practice for the case study, even if we haven't highlighted it as that's what it is. In reality, we've done quite a lot of practice for these case studies. So let's just run through this all the same. So this is from a female athlete before and after a training program. We've got her age and weight and the information that we need to process some expired gas data, so pressure, temperature. We've got the power in the first session. We've got that down here. And we've got the sample duration for all these gas bag samples of 60 seconds. Fine. So in our first test, 60 litres, 17.1 O2 expired, 3.4 CO2 expired, heart rate 173, power 150. In the second test, after the training program, 57 litres expired, 16.8 FeO2, so 60.8% oxygen, 3.6% carbon dioxide expired, heart rate of 172. This time the power output is 170. Both these cases, this was supposed to be 50% of the VO2 max. So, if we process that data, we get something that looks like this for this particular individual. Now, before we get into this, you're going to see this set of text quite a lot in these next few slides. And this is just a framework for you to approach the case studies. So there's 2 questions to each case study. Question 1 is interpret the data. Question 2 is give me some physiological underpinning of the things that you've been describing. So for the first part in the interpretation, we have to consider what's the context. And by context, we mean what's the situation in which this data was collected, because that will affect the interpretation that you put on it. So what's our context? Our context is it's a female athlete before and after a training program. So what does that mean? How does that help us? Well, it means we're thinking that the training program was supposed to improve her capacity somehow. It might be to improve her VO2 max, it might be to improve something else. But certainly we're looking to see whether, if there's been a training program, that's the context, then we want to see if something has improved as a result of that training program. Fine. Her weight hasn't changed. We know that can affect relative VO2 max, so we can discount that if we see any differences. And everything's been standardized like we normally do for gas bag analysis. So context is an athlete who's gone through a training program. What information have we got? Well, we've got all the standard information we would expect. VO2, absolutely. Relative VO2, heart rate we were given. We've got all the other analysis that we might want. So RER, percentage fat and carbohydrate, and so on. So given 1 and 2, given those two things together, given the fact that we expect some kind of improvement, and we've got information where we can decide if there has been some kind of improvement, what would be our interpretation? Well, VO2 is the same pre and post, but we would expect that because it said it was 50% VO2 max. Heart rate's about the same. Well, we would expect heart rate to be about the same at the same relative intensity, and both are at 50% VO2 max, so that's what we would expect to see. RER is the same, and we've seen that in some of the papers that we looked at, that relative RER doesn't change, broadly speaking. So RER at 50% max before training is about the same as RER at 50% max after training, and that's what we see here. The difference is here. So the difference is there's a higher intensity for the same VO2. So they're using the same amount of oxygen for the same heart rate and the same RER, so they're able to produce a higher power output as a result of that. So the interpretation is then that the training that they've been through, we don't know if it's improved their VO2 max. It looks like it hasn't, because our assumption would be it hasn't, because the heart rate VO2 relationship seems about the same, but we've only got one data point. So it's unclear whether VO2 max is improved. Seems unlikely. However, they are producing more power for the same RER, same heart rate, and the same oxygen consumption. And that suggests that whatever the training program has been has had some benefits because they can now produce more power for the same VO2. So the training program has been beneficial, has improved their capacity, but it's improved their capacity in a very specific way. Right? It's not that they've just got fitter or their VO2 max has improved. It's improved their ability to produce power at some sub-maximal percentage of VO2 max, in this case 50%. So that's our interpretation. So the second question then is about physiological underpinnings, and we have to consider what systems have been affected and how has training affected or changed those systems. Well, we know we've got same VO2, same RER, same heart rate, but a higher power output, particularly in that second session. So that tells us that two things have happened. The first is that there must have been some improvement in efficiency, because previously this athlete could use 36.4 mil per kilo and produce 150 watts, and this time they're using 36.6 mil per kilo of oxygen per minute and pushing out 170 watts. So almost no change in oxygen, substantial increase in power output. Therefore, their efficiency, their ability to turn oxygen into physical work, or oxygen and glucose and lipids into physical work, is improved. So that's the first thing. Efficiency must have improved. The second thing is there must have been some of those adaptations that we've spoken about in previous weeks. Because if in this second test they produce 170 watts for the same heart rate and the same O2 and the same RER, we have to assume that in this second test, if we'd drop the power to 150 and match the power output, this heart rate would have been lower, this VO2 would have been lower, and this RER would have been lower. And the only way, certainly we know we can drop heart rate in order to generate the same power, is by having some of those central adaptations. We must have one or all of an increased heart size, increased compliance, so that we get an increased stroke volume, increased cardiac output, so we can have a lower heart rate. That's one of the things that has to have happened. We are unclear if there's been peripheral adaptations, because there's no evidence of extra oxygen extraction. If there was, then we would be able to see differences in O2, but we don't. So, in terms of the physiological underpinnings, we certainly seem to have some central adaptation, because if we'd have matched the power output, we would have got a lower heart rate. And we've also got some efficiency improvements, because for the same oxygen consumption, we are producing higher power output. Okay, so we've seen one example with VO2. Let's have another example. So this is two data sets coming from a tennis player following a flexibility training program. Now, this is actually the same data that I presented in another video that's on Moodle as a separate preparation for case studies. But I wanted to go through this using the same approach of what's the context, what's the information, and how do we use that for interpretation. Because I went through it slightly differently in the other example. So we've got two data sets from a tennis player coming into competition, wants to improve their flexibility, and what's our assessment of their flexibility protocol. So our interpretation process then is, what's the context? So we've got an athlete who wants to improve their flexibility. Yeah, so we say here, that's their aim. They want to improve their flexibility. The context would be different if they wanted to maintain their flexibility, or if there was no mention of flexibility, if they just said these are two data sets. Because if you're looking to improve your flexibility, then you're looking for better measurements in the second time versus the first time. If you're looking to maintain flexibility, then you'd be happy if they're about the same. If you're not mentioning flexibility, then presumably you would be happy if they're about the same too. So our context is an athlete who's gone through a training program. Next part of the process then is, what information do we have? And we have quite a lot in this example. So we know it's a male athlete who plays tennis. He's 24. This first testing session was on the 1st of February in 2019. The second testing session was on the 1st of June 2019. So there's a good few months between these two sessions. Certainly plenty enough time for improvements in range of movement or flexibility to be evident. This first session was done at 10 a.m. on some tennis courts, and he had a 5-minute jog as a warm-up. The second session was at 4 p.m. in a gym, and had 5 minutes on a bike as a warm-up. So there's a few things we might be concerned about already, because they're different times of day, and we know a few things about flexibility in time of day. Core temperature is different. Core temperature affects flexibility. We know flexibility changes throughout the day, so that might affect it. We've got courts versus a gym, and we don't know much about the courts, but gyms usually have controlled temperatures. Courts might be outside, might be cold, particularly if it's in February. Maybe they're indoor courts, probably still cold in the middle of February. So again, we've got differences in temperature that might affect our measurement, but we had a pretty decent warm-up in both conditions, so a pretty decent 5-minute warm-up. What data have we got? So we've just got a couple of measurements: knee flexion, hip flexion, and internal rotation, measured in triplicate with an average and that's done across the board. And our knee flexion goes from 137.3 to 138.3. Hip flexion 139.6 to 141. And hip internal rotation 42.6 to 43. So given one, the context that he's trying to improve flexibility, and two, the information that we've got. So the information is really quite small increases alongside important differences in how those measurements were taken. So what's our interpretation? So interpretation is that there's been some relatively small changes. It's unclear if there's been an improvement because of the differences in testing time and testing location. It would be better if they had the temperature at the time of testing as well. So overall, we would suspect that the training program hadn't worked, hadn't been particularly effective, because over 6 months we would like to see bigger changes than this if the training program had been looking to improve it. Not least because, so if we look at knee flexion, just for example, 137, 138, 137 before training, 138, 138, 139. So it's a very small increase, but one of our pre-training measures is the same as two of our post-training measures. So it suggests that this increase is inside the error of the measurement of the noise that you get just during repeated measurements. Same here, 139, 140, 144. Well, our range in testing set 1 was 138 to 142. So we've got very small improvements. Those improvements in the second session, where it was later in the year, possibly warmer, later in the day, certainly a higher core temperature, and in an indoor location versus an unknown, possibly outdoor location, well, then we would suspect that actually this training program hasn't been particularly effective. These small improvements might just be because of the differences in testing protocol, and they might just be because of it might just be related to the error in repeated measurements anyway. So that's our interpretation. The training program hasn't been effective. So part 2, physiological underpinnings. What systems have been affected, and how has training changed those systems? Well, in this case, no systems have been affected, but that doesn't mean we've got nothing to talk about. We know the systems that they were trying to affect. They were trying to reduce that conservative protection of the Golgi tendon organs and the muscle spindles that cause contraction to oppose, particularly muscle spindles that cause contraction to oppose stretch. So that was what the protocol or the training session was or the training program was trying to do, but it clearly didn't do that particularly well. How has training changed those systems? Well, it didn't change those systems. It didn't improve them. What we did see, if anything, was changes in temperature, which have knock-on effects on muscle compliance and muscle pliability, that allowed for small improvements in flexibility, but certainly not improvements in the magnitude we would expect as a result of a training program. So the systems that we're focusing on, Golgi tendon organs, muscle spindles, haven't been affected. That would have been the aim of the training program. Those systems haven't improved, and any changes we've got are likely due to the physiological effect of temperature on those muscles. Okay, so if we look at just another example, then in this case we have got slightly different. So this isn't before and after a training study. This is just a snapshot of someone's VO2. There's a VO2 max test data. Again, this is the same data that was in one of the seminars. And as I say, the seminars were all around practicing for the case study stuff. What's different is what's the context, what's the individual and situation that you're trying to interpret this data in terms of, and as we've said, both things are important. So, a series of Douglas bag measurements across different exercise intensities, and we have to assume that this last one is VO2 max. So, what's our interpretation? This also, before we move on, this is a VO2 max test from a 28-year-old, 74 kilo athlete, and he wants advice because he wants to compete in the elite men's race in London Marathon next year. Now, to get into the elite race, you need a marathon time. I think it's sub 2.5 hours to be considered eligible for the men's elite. So, part one, what's our interpretation? So what's the context? Context is it's a snapshot that we have to give some feedback on, and we have to give that feedback in terms of the likelihood of this individual being able to take part in the men's elite race. Does his VO2 max suggest that he's there or thereabouts, or does VO2 max suggest that he's a long way off? What information do we have? Well, we've got his age, his body mass, and then we've got the results of each of those different stages of his VO2 max test. And given 1 and 2, what would our interpretation be? His VO2 max peaks out at 57.9, so just on 58 mil per kilo. Peak heart rate's pretty decent at 197. And we're happy this is a max test. If you remember, I said in one of the sessions that to be a max, in a max test, one of the things we like to see is an RER of 1.1, because that indicates you're producing lots of lactate and you're buffering lots of acid, and you're producing excess CO2 in addition to the CO2 from energy metabolism. So we're reasonably happy this is a max test. Heart rate within 10 beats of his heart rate max. RER is nice and high, probably a max test. So what's our interpretation? VO2 max of 57.9. Where does that sit for a 28-year-old? And where does that sit for an elite athlete? Well, if you remember, this table was from, I think it was the first session we did on VO2. So our individual's 28. Here's the column for 20 to 29, so we would fit in here. So your average VO2 max for a 20 to 29-year-old is 47.6, plus or minus 11. So if we add 11 on, we get to what, 48, 58, 58.9, and he's 57.9. So he's within one standard deviation of the average for his age. Now remember, he wants to take part in the elite men's marathon. Elite marathon runners have much higher VO2 maxes than you would find in the average 20 to 29-year-old male. So what's our interpretation? Interpretation that his VO2 max isn't sufficiently high to get to his goal. In order for him to take part in the elite men's race, he's going to have to substantially increase that VO2 max. As a guide, we would normally want to see certainly elite marathon runners above 75 mil per kilo is where we would normally want to see them. So that's part of the interpretation. Any other interpretation? Well, he's 74 kilos. That's not heavy, but it's heavy for an elite marathon runner. They're normally somewhere around 64, 65 kilos. And what we find is, even if he didn't get any fitter, so he's 4.28 litres a minute. If he lost 10 kilos, went down to 64 from 74 kilos, even if this stayed the same, his VO2 max would go up to around 68 mil per kilo. So we could do a lot of good just by losing some body mass. That's not to say he's overweight at all. He might be 74 kilos of complete muscle with no body fat on him. He would still have a higher VO2 max if he lost 10 kilos. Because remember, we just divide this by his body weight, times it by 1,000 to get this. And so to get that, then he would, if he dropped his body weight, that would get him part of the way there. It would get him much closer. The challenge, of course, is dropping body weight but maintaining aerobic capacity. So that's our interpretation. He's got a lot of work to do if he wants to get to the elite men's race next year. needs to substantially increase his VO2 max. He probably needs to reduce body mass at the same time. Physiological underpinnings, what systems have been affected? Well, this is all the stuff that we spoke about in terms of what systems relate to VO2 max, and part 2, what changes those systems. So we know that his max is determined by his stroke volume, which in turn is determined by his heart size and his compliance and his blood pressure. His oxygen extraction is determined by his AVO2 difference, which in turn is determined by the number of mitochondria and capillarizations and his ability to extract oxygen. So they're the systems that he has to work on. And any training that he does between now and successfully taking part in the elite men's race, if that's what he manages to do, will require improving his VO2 max, which in turn will require improving his stroke volume, his cardiac output, his oxygen extraction, so that his overall VO2 max increases. Okay, so that's kind of a brief overview of how I expect you to approach the case studies. There are no surprises, nothing that's supposed to be a trick. There is just, in every case, some data, in every case similar to some data that we've looked at in the seminars. Your job is to interpret that data for me. What do you think it means? And then answer the second part relating to what are the physiological systems either that explain how the person is here or that explain how the person can get to where they want to get to.